Hello everyone, welcome to Dakshana e-classroom program. In last lecture, we talked about different pressure measuring instrument, that is barometer and open tube manometer. So we saw how exactly barometer measure the total or absolute pressure, and basically open tube manometer mainly used for measuring gauge pressure, or it can be used even for calculating or for measuring total and absolute pressure. And we saw next was like Pascal's law. That was all about last lecture. Let's continue here with the new topic, that is force and torque on a dam wall. So like many of you might have seen many dams visited, and you must have been observed something that the dam wall at the top, its thickness is quite low, but at the bottom it thickness is generally normally high. So why that is high, we can understand that too. And if let's suppose this is used in some problem that on some dam wall you are asked to find the force and torque about any point, then how you can calculate? Let me explain you that. It's simple thing. So first thing is, here let's consider this is a dam, and of this dam wall, and height of the liquid water filled in this is water, is let's say from bottom to this is height h, and density I'm taking its rho. Now what is happening outside, this is the open to atmosphere, so pressure will be equal to P naught. Now what will happen actually here, from this top surface, let me say here the thing is that as you are going down, the pressure will be changing, is it? Because pressure, we have seen, it depends on the depth, is it? So P is equal to P naught plus rho g h. So h basically height from the top surface is changing, so pressure will be changing. So pressure will be changing. Then if I consider one strip, then force on that strip as you are going down will be changing. So means here variable or changing things are involved, means in that case we need to go for integration method, right? So let me consider here at some distance y from the top, or I can take it y from bottom also. So let's say this is y and its thickness is dy, because variable things are there, so I will actually consider this strip only of thickness dy, and let me take this as b, dimension as b, this height as total height as h. Then pressure at this point I can write, is it? So this is the, let me write my okay, let me write, this is some point 1, then pressure, and from bottom this is height y, then top it will be h minus y. So pressure at depth of h minus y can be written as what? That will be equal to rho g, and height is h minus y, right? This is the pressure. So force acting on this strip will be equal to what? So the force acting on strip of width dy, that df can be written as pressure multiplied by b into dy, area, right? And p is rho g h minus y into b multiplied by dy. Now it is asking total force, then I can integrate it simply. So this can be integrated from where? 0 to total f, and this will be like y from 0 to capital total h. So this integration, let me simplify, it will be simplifying f on this side, this is rho g b, it is simply out, and this is h is also constant, so integration dy will be simply y. So this is h y minus integration of y is equal to y square by 2, substituting the limit 0 to h. So 0, everything will be 0, and h, it will be h square minus h square by 2, so overall it will be h square by 2, and then this is equal to rho g b h square by 2. This is the total force on the dam wall, on dam wall. So you can see it's a simple thing is there. So if anywhere you required, you can easily apply exactly this way and you will get the answer. Similarly, if torque is asked, so torque on wall, the point about torque is that we must define that about which point, about which line we are interested in calculating torque, is it? So let me say torque about this bottom line, is it? The torque on wall about bottom line, right? So again, because force is variable, so due to if I say force at this point, then torque due to this element about this will be different than any other element. So again, for torque also we need to integrate. So I got the force on this small strip. Let's calculate torque about this bottom line due to this df. So we already got df is equal to rho g b, this is h minus y into dy. Then torque due to df force about bottom line of dam wall, so that can be written as df multiplied by distance, that is y. Okay, so then I can write d tau is equal to y multiplied by df, and that is equal to rho g b h minus y into dy. Total torque, simple integration, limit 0 to tau, 0 to h, 0 to h, we can simplify it. Tau is equal to rho g b, and this is integration hy minus y square into dy 0 to h. So hy it will be integration, so this is rho g b h y square by 2 minus y cube by 3 0 to h. H 0, everything will be 0. H, it will be h cube by 2 minus h cube by 3. LCM will be 6, 3 minus 2, that will be 1. So tau we are getting, this is rho g b h cube divided by 6. This will be the torque. So you can even directly remember this result if it is, this is the case. If something is like little bit changes are given, then you need to follow the approach. So not much changes asked in your like your exam, so that's why like these standard results you can like remember for force and torque on a dam wall. So this is just sort of like one of the example or application of calculating force, is it, due to fluid or liquid on some wall, and torque also. So let's see the next part. Okay, next is pressure in accelerated fluid. So basically we have already seen variation of pressure with depth. In that case, our simply container was placed at some like rest anywhere, and then we check that as we go down deep in the water or in the container, in the liquid, pressure keep on increasing, and we calculated that p by dy was coming out if I am measuring y from the bottom, is it? So let's say if I am going y, and is it, in this case small element is considered of thickness dy, then in y direction pressure varies, and we calculated here dp by dy equal to minus of rho g. If you are measuring y from the top, then it will be plus rho g, because it's saying as y increases, what will happen, the depth will decrease. So with depth pressure increases, so going up pressure will decrease. So this is the, and by the property of fluid I told that pressure at same level, is it, pressure at same level will be like equal at all point in the fluid. So if you are taking pressure at this, all these points are at same liquid at same level, then pressure will be equal. So that's why I can write pressure variation dp by dx, sorry, will be equal to 0, right? Same point. So this is the case, like here pressure in accelerated fluid, here we, or I mean that a container which is accelerating, maybe you can just imagine one situation. Let's suppose one container is placed in a lift and which is accelerating down and up. So what will be the variation of pressure with depth and height in that fluid? It's not that fluid is flowing in the pipe with some acceleration, not that case. Okay, so your container is accelerating. So this is the one case. Let's, if I consider ax is equal to 0 and ay equal to 0, so means when there was no acceleration, in that situation this is the relation, and we derived p in y direction is equal to p naught plus rho g h, where h is the depth from top surface. So this relation we already derived, and pressure at any point will be equal to this, and in x direction as you are moving there will be no variation. Here we are interested in knowing the pressure if this container is accelerating, is it? So let me consider the case. Again, the point is that for you people the final result is more important, because you will be required, most of the time problem will be straightforward, directly formula based. So if you're remembering the formula, you will be able to solve, you will be putting the values and you will be getting the answer. But still I will try to explain you that how we get that relation, so that you can understand it better. You don't have to worry about its derivation part, you don't have to like think much about that how we get the relation. That is additionally for your understanding purpose. If you are getting it, it's great. If not, then finally just remember the result. Okay, so let me try to explain you. So in this case I am considering a condition where, let's say, ax is still 0, means there is no acceleration in x direction, and there is acceleration in y direction. So means ay is non-zero, or I will say ay is, let's say, equal to a. So again consider this container, and let me draw it there because I will require it large. So this second case I am drawing it here. So we have this container and it's accelerating in y direction. So let me say acceleration is in upward direction. This is the container. Maybe the situation you can imagine very easily is this container is placed in lift. Okay, so this is now how we get the result. If you want the result, I can directly write, actually in this situation dp by dy become your minus of rho g effective, and g effective, if acceleration is upward, in that situation g effective is g plus a. This is the result. But how we get it, let me tell you that too. So here what I can consider, just consider one imaginary or cylindrical element inside the fluid. Consider a cylindrical element inside fluid. Now this element will be like, with respect to this frame, it will be at rest, but let's say here again this is at y, this height is dy. Actually this element will be like very small, but just to show you so that you can see it visibly, properly, clearly, I have drawn it bigger, a little bit large. So here I am saying let the pressure is p, at this point its pressure is p plus dp, right? Now from ground frame, what you will say, because the system is accelerating, so if you just focus only on this element, do you feel the acceleration of this element also? Yes, because it is accelerating, right? System is having acceleration, so if your focus is only on this small element, then that element will be also accelerating because it's moving with the system, right? With the lift, with the container. So from ground frame, right, what I can write, net force F net must be equal to mass into acceleration. And what is the net force? Net force, so upward force, it's P into, let's say, its area of cross section is capital A, density of the liquid is rho, Okay, height of this cylindrical small element is dy. Then I can write upward force is P into A, downward force P plus dP multiplied by area, and one more force will be there downward, that is weight. So weight I can be writing rho density multiplied by volume A dy. So this is m into g. And if, because we can see from ground frame this element is having acceleration, so what I will write, net force is equal to ma, and m is equal to rho A dy multiplied by A. I hope you must be clear with this relation. Simple. I don't think there is any big problem. There should not be any confusion in this relation. What I'm writing, simply I considered one small element inside fluid of same fluid, and this element, as I'm seeing it from ground frame, so the system, the container is accelerating, so with container this element will also have same acceleration. Then I'm writing net force equal to ma by Newton's second law. So net force, upward force, pressure at this point multiplied by area, downward force, pressure at that point multiplied by area, its weight, density multiplied by volume into g, net equal to mass into acceleration. Simplifying it further, this is PA minus PA minus dP into A minus rho A dy g rho A dy into A. Clear? This cancelled out, A also cancelled out. We are left with minus of dP. Let me send this term this side. So we are left with rho A plus rho into g, and dy will be also there, taking dy common, so dy. Dividing dy, taking rho out and sending the negative sign that side, we are getting dP by dy is equal to minus rho into g plus A, and this you can write minus of rho multiplied by g effective. That's what exactly. So the result is this, which is simple, straightforward, right? So means if a container is there which is having some fluid filled and it's accelerating, it can be upward and downward. Then if it is accelerating upward, then you must be remembering that g effective becomes g plus A. If the system is accelerating downward, maybe your lift elevator is accelerating downward, in that situation effective g becomes g minus A. A is the acceleration of lift or elevator. So here I am considering the situation where it is accelerating upward. In that case, we even by derivation we are getting it, g effective is equal to g plus A, correct? And this is the pressure. So now here, if you are asked in this frame, in this container, if you are asked to find the pressure at depth, let me just erase this part. So just consider this is the same system, and which is accelerating upward with acceleration A, and now you are asked to find pressure. Let's say this is a point 1 at depth h. This is accelerating. So what is the pressure at point 1? Pressure at point 1. So here if it was not accelerating, then pressure was what? P naught plus rho g h. If it is accelerating, then g is replaced by what? G effective. Rest everything will remain exactly same as it was earlier, is it? So in this situation you will get P1 is equal to simply P naught plus rho into g effective into h, and this will be P1 equal to P naught plus rho g effective is g plus A multiplied by h. This is your answer. You can get it by integration also, dp this into dy, exactly taking 2 point y1 y2, one at top surface and taking pressure at that point P naught and integrating it, you will get still same result. So this is the situation. So similarly I can write if acceleration is downward, in that case g effective will be equal to g minus A, is it? So the same container, but its acceleration, it's filled up to here, it has acceleration A downward. In that situation this is y dy. So in this situation your dp by dy will be minus rho into g effective, or you can write this is equal to minus of rho into g minus a, because acceleration is downward. Then g effective become g minus a. So this is the situation. So means if acceleration is given in y direction, whether it's upward acceleration, downward acceleration, in every situation you should be able to find the pressure inside liquid at any point. If you are asked to find the pressure difference, then get the pressure both the points, simply get the difference, that will be your answer for. So this is the condition for pressure in accelerated fluid, but here I have discussed only one part, when acceleration is there only in y direction. Let's see the next case. If there is acceleration in x direction, what will happen? Okay, so let's consider fourth case, when ay, here I have made that equal to 0, means there is no acceleration additionally in y direction, but ax is equal to a, which is non-zero, means there is some acceleration of this container in x direction. So let's say this is the situation when simply container is resting or in on rest, no acceleration in any horizontal direction. We know the free surface will be just like this. Now let's say I have given some acceleration a in x direction. Just for a moment think about the free surface of this liquid. Now you must be understanding what is the free surface. So the surface of the liquid which is in contact with the air is termed as free surface, because liquid will have many surfaces, which is like these surfaces are inside, so this is not free surface. Only this top surface, top layer will be a free surface. So do you think like the free surface orientation will be still horizontal? Is it? Let me just think, let me tell you something. So let me consider one small element here on the free surface. What will happen if I looking at this element, let's say from this frame, is it, from the frame of container, on this element force acting is mg, if m is its mass, because x container has acceleration a in right direction, so there will be also pseudo force in, and that will be like ma, right? So because mg is like acting normal to the surface, and we know that liquid can bear normal stress, so there is no problem with mg. But I am assuming that this element is still there. If it is still staying there, then what will happen? Horizontal force will come. Horizontal force ma, and if this element is having some small area dA, then there will be what? Horizontal force means it's basically tangential force divided by that area dA. There will be tangential or shear stress. But can a fluid bear shear stress? Definitely no. It will be violating even its basic definition of fluid. So then what will happen actually? You understanding? Here what I did, I assumed that even when container is accelerating, I assume that the free surface is still staying there. If it is still staying in same position, then there will be, is it, if free surface still stay horizontal, then there will be shear stress. But fluid can't bear shear stress, so this is contradiction. So first thing is, now the point is that the free surface will not remain horizontal anymore. So when the system is given some horizontal acceleration, actually the orientation of free surface changes and it becomes something like this, right? and we can even calculate exactly at what angle theta this free surface will incline. And if acceleration is in this direction, you must be even understand, you will be clear that the free surface will be in this shape. If acceleration is in this direction, then free surface will incline in this manner. So it will incline in a manner such that this small element, now what will happen? One force is acting mg, another force pseudo is ma. The free surface will incline in a manner such that the net force is coming normal to this free surface, because normal stress fluid can bear, but it cannot bear any amount of shear stress. So it will align, the free surface will align itself in a manner such that total shear stress is eliminated. It is only and having only normal stress. Is it? So free surface of liquid align itself such that it has only normal stress, or you can say the net force on each of small element of fluid must be normal, or you can say must become normal to free surface, and so that it's not violating the definition of fluid. So because of that, free surface will align at some angle, right? So that is one big point here. When there is acceleration in the x direction, free surface will not remain just like earlier case, just like horizontal. No, it will not remain, it will align at some angle. Next question comes is, what will be that angle? Can we calculate? Yes, we can. So let me tell you how we can calculate. So the angle of alignment of free surface, so that first thing is, from its definition, liquid will align its free surface in a manner such that net force become normal or perpendicular to its free surface, like this. Is it? So if this is the situation, then I can write this theta will be equal to this theta, and net force, so this net force will be along this is mg, then this will be ma. So then I can write tan of theta will be equal to what? Ma divided by mg. This implies theta is equal to tan inverse of a by g. So we even got the value of theta, value at which the free surface will align itself when there is acceleration in horizontal direction, right? Exactly in same manner, if I consider another case, let's say this is the container which is initially filled like this, and it is given acceleration a in this direction, then the free surface will align in this manner, right? So free surface will align in this situation, in this direction, and this theta will be still, tan theta will be equal to again a by g, and theta will be equal to tan inverse of a by g. So this is about just alignment of free surface when container is given some horizontal acceleration or acceleration in horizontal direction. Next point is still there, what will be the pressure variation when there is acceleration in horizontal direction? So let me tell you that. So in this situation, when AX is non-zero, first thing is the free surface will align at some angle, and we already got this angle theta, that is equal to theta, we already got theta is equal to tan inverse of A by G. Okay, so now next thing you can see is that because the height is also different, so definitely now at same horizontal level, at this point and this point, pressure will not remain same. Is it? So in this situation, because now there is acceleration, so let's say this is 0.1, this is 0.2, so now at same horizontal level, pressure will not remain same, right? Means there will be some pressure difference. Next is what will be that? So one way is, if this is x, length of this element is dx, the result is earlier dp by dx was 0 because there was no acceleration in x direction. In this situation, here pressure will be low, here pressure height will be, height is high, so pressure will be high, so this minus this, it will be negative, so it will be equal to minus of rho into ax. Simple. Is it? If you want the derivation, if you want to understand it, you can exactly go in same way. Let's say pressure here P, pressure here P plus dp, area of cross section A, then I can write net force is equal to ma. So net force equal to m into acceleration, so area of cross section, length, so net force will be P into A, right direction force, left P plus dp multiplied by A, and there is no weight in horizontal direction. Mass of this element is rho into area into dx, rho A dx, volume into ax, mass into acceleration. Just simplifying it, PA minus PA minus dp into A equal to rho A dx into ax. This cancelled, A cancelled, dividing by dx, sending that negative sign there, we are getting dp by dx is equal to minus of rho into ax. So simple, this is your result when there is acceleration in x direction. So by this you must be clear that even if the container is accelerating in any situation, accelerating upward, accelerating downward, horizontal, left, right, what will be the pressure at any point, pressure variation, we should be able to answer that. This is your pressure variation in the case of x direction when acceleration is there present, or acceleration in x direction is non-zero, right? So this is about pressure in accelerated fluid. Here comes one more case, is that, let me show you that with an example. Okay, so consider this case. A cylinder containing liquid of density rho is rotated with angular velocity omega. Find the shape of free surface. So let's say this is the cylinder containing liquid of density rho, and initially it was at rest, then shape of the free surface will be like this. Now what will happen once it is rotated with angular speed omega? What will happen? The free surface will align itself in a manner such that net force at any point must be normal to free surface. Is it? Because you can see, if like these elements will be rotating in circle, then they will have centripetal force or centrifugal force outward. So the free surface will not remain anymore like this. So actually the alignment become like this. Here the alignment of free surface will be something like this. Just wait. The free surface will become something like this, because here you can see actually this is the bottom. So let me take, this is origin and this is x-axis, this axis as y-axis. Now what will happen if I consider one small element here? Is it? Let me show you, because otherwise it will not be visible to you. So the free surface will be something like this. Is it? Here This is the axis of rotation. So now in this situation, what will happen? Let's say this is one small element of mass m. It will have force mg and it will have centripetal force, that is m. If I take this element is at a distance x, then mx omega square will be the centrifugal force. So the alignment, the surface will align in a manner such that net force, this net force must be along normal to this surface, because with x what will happen, this force will keep on changing, so that's why the surface, the curvature will keep on changing, so it becomes something like this. Now let's say from x distance, if this angle is theta, this is total 90, so this will be also theta, right? Then first let me get the theta. So what I can write here, let me write it here only, tan theta will be equal to what? Because net force, the alignment will be in a manner such that net force is along this normal to tangent to free surface, is it? So this is the net force, then I can write this is equal to what? Mx omega square, and this vertical is mg. So here you can write this is equal to mx omega square divided by m into g. For a small element I am taking its mass equal to m, is it? So m is mass of small fluid element. Okay, so then this simplifying, we are getting theta or tan theta, we got this is x omega square by g. Next thing is, if let's suppose, because this will be a curve, so I can write this will be like one curve, then it will have some relation y is equal to some f of x will be the equation of this curve. Then what will be dy by dx at this point? So coordinate here, this is origin, so coordinate of this point will be y comma x. So let the free surface is a curve in the form of or function of curve with of y equal to fx. Then this is the point whose coordinate is x comma y. Then I can write this implies dy by dx equal to what? Slope of fx at x comma y, and this slope is also equal to what? Tan theta, right? Dy by dx is equal to, and this slope is equal to what? Tan theta. So you can write tan theta equal to slope equal to this equal to x omega square by g. Simply multiplying it and integrating this implies dy equal to x omega square by g into dx, integrating 0 y 0 x 0 y, integrating it we are getting y is equal to x square omega square by 2g. So this is the shape of free surface, so it is a parabolic, right? Now next question, from here the pressure will be equal to what? P naught. Here pressure will be equal to what? P naught, and at this point height is what? Y. So pressure at this point I can write will be equal to P naught plus rho gh, is it? So exactly here this is let's say element at distance x, then is height y. I already got equal to x square omega square by 2g. So pressure at this point P, then P can be written as P equal to P naught plus rho g y, that is P naught plus rho omega square x square by 2g. This is pressure at this level at distance x from axis of rotation. So this is all about this case of rotating cylinder about its axis with angular speed omega. First thing, free surface become a parabola. What will be the equation? That you can write x square omega square divided by 2g. If you are measuring this distance from axis as r, then this y will be equal to r square omega square by 2g, is it? And pressure you can write, because you got pressure, this is open to free atmosphere, pressure will be P naught. At this point it would be P naught plus rho g h. H is y, so that is simple, P naught plus rho g h, and h is here y, and y you can substitute here. So this is the pressure at any point. This is all about pressure in accelerated fluid. Okay. Okay, see next problem. So here find the difference in height of liquid level in two arms if tube is accelerated with acceleration a in horizontal direction. So this is the situation, a tube U shape given and some liquid is filled in this tube, so that it's like equal initially, the level of liquid in both the arms will be equal, and initially it is at rest. Now it is given some acceleration a in horizontal direction. Now you can imagine that after the acceleration is given, the free surface will not remain, or level of liquid in these two arms will not remain in exactly same level. What will happen? It is accelerated, so the free surface will try to align at some angle. So after that, let's say the level in this drop up to here and level in this tube rises by some amount, so that final here it become, let's say, y level y2, and level of liquid in this arm is y1. So then in this situation we can imagine like this is the alignment of free surface. So what will happen? This will be equal to theta, because here there is no space, so the liquid cannot be there, but the level in two arms will be in such a manner so that the free surface will be at some angle, and this theta we know already. So here if this is y1, this is y2, then we can easily solve it. So first thing is, what will be tan theta? Tan theta we know is equal to what? A by g. And tan theta can be written in terms of y1 by 2. So this is equal to what? Tan theta, this height will be equal to difference in, like this will be equal to what? This is y2 minus y1, and this base is, so this is equal to y2 minus y1 divided by L, and this is what? The difference in level of liquid in two arms, and this is what we need. So this implies y2 minus y1 is given by simply A by G multiplied by L. This is the answer, so easily you can calculate. Okay, see the next problem. So find the maximum acceleration in horizontal direction so that liquid does not spill out of container. So here we have a cubical container, and 2/3 of this container is filled with liquid of density rho, and this side is A, this is also A, and this is also A. Now let's say this is given some acceleration ax, and we are asked to find the maximum acceleration value or maximum value of acceleration ax, so that the water does not come out of this container. This container is open from the top. So what can be the maximum thing? Like maximum it can come up to here, so the level will be like this. If I look at it from front side, let me draw the diagram, then the liquid level in the container will align like this. So initially it was like this. This is filled up to 2a by 3. Now what will happen? Maximum it can go up to here. So this is rising by what? A by 3. Symmetrically I can say it will fall here by A by 3. And this is how much? A. So now we can easily get, this is the angle theta, right? Straightforward we can, by just, because volume of the liquid will shift from here to there. So this will rise by A by 3, so exactly A by 3 it will fall, because this is the only maximum space available here, height, that is A by 3. So liquid will shift from here to there and the free surface will align in this manner. So then again you can write tan theta will be equal to what? That will be equal to ax by g, because if here you can see if acceleration is going beyond that, it will try to align even at higher angle. In that situation you can see ax increases, theta will also increase, so it will come down and it will come up, and then liquid will come out, and we don't want that. So this is the maximum situation, like big condition. So tan theta is equal to ax by g, and tan theta can be also written as, this is equal to how much this height is, that is 2a by 3. How much is this? So this is also equal to 2a by 3 divided by a gets cancelled. This implies maximum acceleration is 2 by 3g, and this is the answer to problem. So that is how usually we can, if you are understanding the concept, you are clear with the concept, These are problems are straightforward, simple, you can answer easily. Let's see, the next topic is Archimedes principle. Okay, so next is Archimedes principle. Archimedes principle is a sort of like one principle or one of the like observation, experimental observation. So let me just first tell you what exactly like we can even observe, and that was exactly first time observed by Archimedes, and he gave one statement what the result he was observing. So here what is happening, let's consider this is a object having density rho, volume v is the volume, and initially let's say I'm hanging it in the air with some spring balance, then the weight shown by this spring balance of this body is, let's say, W1. What will happen simply if you are the same object is now submerged like in this liquid, is it? So this is a spring balance, and the object is now submerged in the liquid. Here I am submerging it like immersing it completely. There is maybe possibility that it may be partially submerged. So what will happen, because initially this container was filled with liquid of density sigma, so this liquid, when this object is submerged, liquid will flow out, and that will be coming out in this container, small container. Let's say I am taking that in small container. So first thing is what we observed is the reading of this spring balance will change by W2. Another basic thing you can understand is that we know at this point there will be some pressure. At this point pressure is P naught, this point pressure P naught, P naught, P naught, P naught. So everywhere there is no net force coming on this object. Net force coming is cancelling out. Whatever its mg weight is acting, that is exactly shown by this spring balance. But when it is in this like inside the liquid, pressure at this point will be different, pressure at this point will be different, and you can see pressure at this point will be higher, P naught plus rho g h1, P naught plus rho g this h. So here pressure is high, and that too it will be upward. So you can just imagine there will be net upward force will be acting on this body, is it? We call that as actually buoyancy force. So question comes is what will be that force, is it? So first thing is what we did is we consider this system spring balance, and reading we take when the object is completely submerged, and this is your W2. This weight is taken, like fluid is taken out, and this weight of this fluid, this liquid, is measured. This is all simple experimental observation, and what we found that this W1 minus W2 is coming out to be weight of this displaced liquid. Right? Simple observation. Practically, even we can prove it mathematically also. So the principle from here is that Archimedes actually for the first time, like he observed and he stated that when an object is submerged in a liquid partially or completely, liquid apply a force on the object in the upward direction. That force is called as buoyancy force, and the force is equal to the weight of displaced liquid. Means when an object is submerged, it's displacing, because initially at this point, this space, what was filled there? It's liquid. So when an object is submerged, it is displacing some liquid from its place. So the force acting on this body in the upward direction will be equal to weight of this displaced liquid, and that we can even getting it experimentally. I will tell you how exactly we can even get the same relation mathematical terms also. So let me first write. So if an object is submerged partially or completely in liquid, it is buoyed up by a force due to liquid called buoyancy force, that is equal to the weight of displaced liquid, right? So when an object is submerged completely or partially in a liquid, the object is buoyed up, means a force is applied on the object in the upper direction, we call that buoyed up, and the force is termed as buoyancy force, and this force will be equal to the weight of displaced liquid if it is partially submerged or completely submerged, and this is termed as Archimedes principle. And now here one more thing here we can see is that, so this is true weight. When weight of the object is measured in air, this is called true weight. When it is measured by submerging in the liquid, then you can see definitely W2 is less than W2 is less than W1. W2 is the weight of liquid by submerging object when it is submerged in liquid. So this weight is less, right? And this W2 is called apparent weight because it's not true weight. So W2, it's called apparent weight of object. Okay, so this is apparent weight, and apparent weight we can write mathematically, this is coming out to be W1 minus W2, and this is equal to weight of displaced liquid, and that is coming out to be buoyancy force. And here how much, what is this, how much? So volume of displaced liquid is equal to volume of object. Mass of displaced liquid will be volume multiplied by sigma, weight will be multiplied by g. So this will be equal to how much? V sigma into g. Clear? So this is apparent weight, and apparent weight can be written as W2 is equal to W1 minus V sigma g, or you can write W1 minus F buoyancy force. This is apparent weight. So even like sometime you are asked to calculate the apparent weight. Apparent weight means true weight minus buoyancy force will be the apparent weight of body. So this principle is called as Archimedes principle. Let me show you this also in mathematical term or mathematical proof also. So consider again here, this is a container containing some liquid, is it, and filled up to here, density of liquid is sigma. So now let me say one object is submerged. Let me consider here this is a object of some cubical shape. So here height of this is let's say h, area of cross section is a, its density is rho, right? So let's say this height, let me write it h1, and this will be how much? H plus h1. Pressure at this point, so will be acting some, let's say P1, and here it will be P2. So force, right? Or this side, they will cancel out. So let me calculate net force acting on this body, is it? So force acting on submerged object. So I can write force is equal to this F2 minus F1 will be the net upward force, means F, or I can write F upward minus F downward. So that will be only if I'm just wondering, I'm just calculating the force applied by fluid. I'm not calculating net force. I'm not considering its weight. I'm just simply calculating force applied, net force applied by the fluid. Is it? So horizontally there will be no net force, only vertically there will be force. So first thing is P1 you can write equal to what? P0 plus rho g, sigma g h1, and P2 will be equal to what? P0 plus sigma g h1 plus h. So then F equal to F upward is P2 multiplied by area, downward is P1 multiplied by area, substituting P0 plus sigma g small h plus h1 into A minus P0 plus rho sigma g h1 into area. Simplifying it, this will be complete bracket. So this comes out to be P0 into A plus sigma g HA plus sigma G H1A minus P naught A minus sigma G H1A. Sigma G H1A, sigma G H1A, P naught A cancelled out. And what is this? So this is upward force or net force that is coming out to be sigma, let's say A into H into G. What is this? Volume. Sigma is density, is it, of fluid. So this is volume displaced, and this is coming out to be sigma into V into G, and that is equal to weight of displaced liquid. Right, so that we can prove even mathematically also. This is Archimedes principle, that when an object is submerged in a liquid, it is buoyed up by the liquid, and this upward force is called buoyancy force, and it's equal to the weight of displaced liquid. Similarly, exactly in same manner, we can even prove it for partially submerged body too. Okay, let's consider next case when the object is partially submerged. So let's say only hi is the height of this object which is submerged, and then I can write again horizontal net force will be cancelled out. Downward force on this side, it will be like this, let's say F naught, and this will be upward force F1. So I can write, first thing is F naught will be equal to what? P naught into area of cross section. F1 will be equal to P naught plus sigma G Hi multiplied by A. So F net will be equal to F1 minus F naught, that is coming out to be P naught plus sigma G Hi into A minus P naught into A. This is P naught A minus plus sigma G Hi A minus P naught A. This cancelled out, that is sigma into Hi into A into G. Now what is this? Hi into area of cross section, that is equal to immersed volume or part of the volume which is submerged, is it? So this F net upward is coming out to be sigma into Vi into G, that is also equal to weight of displaced liquid. So this prove all like Archimedes principle, that in every situation when a body is submerged partially or completely in a liquid, it is buoyed up by a force, buoyed up by the liquid, is it? That buoyancy, that upward force is called buoyancy force, and the magnitude or the force is equal to the weight of displaced liquid when the body is submerged, whether it's completely or partially, and this is called completely Archimedes principle. Here you must be even clear with the true weight and apparent weight. So what is happening when object is hanging in the air, then the reading of spring balance will be a true weight. When it is submerged in water or in some liquid, what happened in that case? The true weight is not readed, is it? The spring balance will be reading something like false weight, actually you can say, or we call that as apparent weight, because that will be equal to true weight minus upward force or buoyancy force. So that's why we can define apparent weight is equal to weight or true weight minus buoyancy force. This is called simply apparent weight, and this is all about Archimedes principle. Next, let's see. Okay, let's continue from here onward in the next class. Thank you.